Today is the last session of this webinar training course about PV energy. So, we hope that once we finish with this today's presentation, you will have a good overview on the solar energy field and its possibilities. Today, we will talk about off-grid facilities. This means those facilities which are not connected to a grid, and they are normally used to feed consumptions in rural areas. As we will study, they have some difference with the grid-connected facilities. For example, that they use batteries and they have to use a special kind of inverters. This type of installations are also called stand-alone installations. So, today's index is as follows. We will start with a brief introduction to this type of systems. Then we will study the main elements in these systems. We will focus in the storage system and the backup system. Then we will see the trends nowadays for this type of systems. We will do a brief overview on the hybrid systems, the efficiency and the smart grids. We will continue with some examples of application of this kind of facilities, and we will end the session with the design and maintenance of one of these projects. So let's start with the introduction for this type of facilities. Here you have a diagram, a basic diagram that can show you the main elements of an off-grid facility. You can see that we have PV modules like we used to have in grid-connected facilities, but now we have two new types of devices, which are the PV regulator and the battery. We will study what are they used for during the next slides. Then we have a special kind of inverter, and we can check that we have two types of different consumption: the direct current consumption and the alternating current consumption. We will check about it later. So, during the next slides, we will talk about the main difference between a standalone facility and a grid-connected one. There are three concepts that we have to keep in mind for making the difference between both types of facility. First, that in this kind of facility an electricity storage is required, as our plant will not be connected to the grid, and it must be designed to supply energy 24/7. So this means even when there is no sunlight, we have to produce energy. So in order to do this, we need to introduce two new types of devices, which are the regulator or charger, depending on the types of installation. We will talk about it later, and the batteries. Second, the inverters must have the capacity to create a grid. This is because they are not connected to any existing and stable grid, so they have to create their own grid. If we continue with the third, in this type of projects, our main goal is to supply energy during the whole year. But we will go back to the previous slide in order to comment that for facilities with consumptions which are lower than 2 kilowatts, we may require modules which have special characteristics, because in this type of installations we usually use DC 12-volt modules. So these modules in fact produce a voltage of 18 volts. We have to know that normally the modules produce a voltage between 30 to 32 volts. So these types of modules are more expensive, but we can maybe reduce their costs, because then we don't need regulator with power maximizers. Anyway, we have to check with the manufacturer both possibilities in order to see which one is the most profitable for our project. So, going back to the criterion of winter production maximization versus annual production maximization, we have to know that in grid-connected facilities, all the design was done in order to get the maximum energy production during a whole year. Now, this concept changed. Why? Because we want to have energy during the worst day of the year. So we need to produce and supply energy to our consumption by ourselves with this PV facility even in the worst period of the year. Obviously, we can help our facility with other mechanisms such as a backup system based in a diesel generator or any other kind of generators, but even if we are doing this, we have to take into account that we have to consider the worst day of the year. For example, in the table chart that you have in this slide, you can see that the worst month of the year in Madrid would be December, with a production of 2.15 kilowatt hour per day. Yeah, but if we choose a different tilt, we can optimize the production during this month and get it to 2.4 kilowatt hours per day. Even if we are losing production during the total year, we have to consider that this might be interesting for us, because we don't need maybe so much production during the summer days. So, during the next chapter, we will study the elements in this type of PV facilities, standalone facilities, focusing, as we said, in the storage system and the backup system. So, the first element that we will study is going to be the inverter. About the inverter, we have to take into account the following considerations. Normally, we can find lower range of powers than for grid-connected facilities if we are talking about inverters for stand-alone facilities. This is because they have to have the capacity, as we have said, to create their own grid. They cannot take an existing grid and just inject their power. They have to create their own stable grid for consumption. So, some manufacturers offer us the possibility to connect in parallel or series several inverters, as we can see in the table at the bottom of this slide. And also, some manufacturers prepare their inverters for auxiliary inputs in parallel in order to have hybrid systems with diesel generators or with wind generators or any other kind of generators. For example, here you can find a table with the main manufacturers of this kind of inverters. We have chosen three types of manufacturers, which are Santrex, Victron, and Ingeteam. If you check the values in this table, you can see that the power per unit is really low. It goes from 6 kilowatts to 15 kilovolt ampere, but the system power is a little bit higher. This is because, as we said, we have the possibility to connect several inverters. In the case of Santrex, we can get to 6 inverters, 2 in parallel and 2 in series. In the case of Victron, we can connect 10 inverters, and in the case of Ingeteam, we can connect 8 inverters. So we can get to a system power just giving a 3-phase signal of 36 kilowatts for Santrex, 100 kilovolt amperes for Victron, and 120 kilovolt amperes for Ingetm. Other observations are that some of them include battery charger, the most of them in fact, and some of them also allow other give us other tools, like for example the Santrex, that allows us to inject surplus generation to the grid, or the allowance of different configuration modes in order to manage the generation and the consumption. Talking about the regulator, we can say that its main mission is to charge the batteries. It is important to make the difference between two types of regulator, what is called a regulator and a charger. A charger is only used to charge the batteries. It doesn't regulate and stabilize the signal, but a regulator is used both for charging the batteries and also to produce a stable signal in order to be used by DC current devices. Anyway, these kind of devices are used both to protect the batteries against overcharging and to avoid excessive discharge within a cycle of the batteries. Normally, in order to protect this device and the batteries, it is recommended to work with an oversizing of 125%. We have to know that these are not simple devices. Sometimes we have seen proposals of PV installation without using these devices, as the panels produce already DC current and the batteries do need this type of current. But we have to know that the battery charge depends on many factors, and this kind of devices have multiple algorithms in order to optimize and protect the battery charging. It is important, very important, to use them in our PV project. Now that we have settled the main concept of we get to the batteries in this point, which are one of the main elements of an off-grid facility. As it said in this slide, the batteries are used for storing the energy that is produced by the modules during the day for being consumed in the periods that there is no solar irradiation. So, a battery is composed by several cells, normally of 2 volts each, which are connected in serials to get to compose a whole battery that can vary between 12 to 48 volts. Normally, we can find batteries in the market for 12 volts, 24 volts, or 48 volts. Also, we can just buy one of the cells of 2 volts and then do ourselves the parallels and serial connections. But the voltage that we normally use in PV applications are 12, 24, or 48 volts. Normally, the system is designed to store energy for several days of consumption in order to protect ourselves of several days of low radiation, because it can happen that there is several cloudy or rainy days and then we don't have energy after 2 days of rain. So 3 days can be a good recommendation depending on which is the location where we are and the price of our PV project. If not, we can consider using a diesel generator as a backup, as we will see in the next slides. So, now we have done an introduction to the main concepts of what a battery is and what is it used for. We will try to explain some considerations that can be very useful if we want to design an off-grid facility. First, we will talk about the battery capacity. The energy that a battery can store in itself is called the battery capacity. So it's a measure of energy, and it is defined as the electricity that can be obtained during a full discharge of a completely charged battery. The capacity in ampere hours is the current that the battery can supply multiplied by the number of hours in which the above-mentioned current is delivered, referred to a certain voltage. For example, a battery of 200 ampere hours and 12 volts could be able to store theoretically 2,400 kilowatt hours. Then we have to consider battery losses and system losses, and so we could estimate that the real storage could be about 1,900 kilowatt hours. Anyway, there are other considerations to be taken into account. One of the most important considerations is about the cycles of charge and discharge. So, here you have an example exposing that theoretically a battery of 200 ampere hours might supply 200 amperes during an hour, or it could supply, for example, 50 amperes during 4 hours, and so on. However, in the reality, the capacity of the battery can vary according to the time that we are charging it or discharging it. For example, if a battery specifies a capacity of 100 ampere hours and we discharge it during 8 hours, then we can get what it is specified, 100 ampere hours. But if we discharge it during 20 hours, it may produce, as you can see in this slide, 116 ampere hours. So, normally a good practice will be considering that if we discharge a battery for a longer period than the period which is specified in their data sheet, we can get more energy from the battery than the one that it is specified. Anyway, every time that we want to buy a battery, it is specified if the energy, the capacity, it's considering it specifies the number of hours for that capacity. For example, after the capacity of a battery in the specification sheet, it will say C8, C10, C20 or C100. That C whatever refers to the amount of hours that they are practicing in order that they are taking into account in order to get that capacity. Another important point to consider for a battery is the depth of discharge. This is the percentage of the total capacity of the battery that can be used without need of recharge and without damaging the battery. Sorry if I read some of the slides, but they are definitions from the manufacturer, and we have to know them exactly as they are defined. So, also we have to know that as a general rule, the less depth of discharge is reached in every cycle, the longer the battery lifetime will be. This consideration depends, as we will see, in the type of battery. But, for example, if we keep our battery to an average discharge rate of 10%, it can last double the years than if we consider a discharge rate of 20%. We have to consider this during the design of our PV project, because obviously a lower depth of discharge means more batteries, and so increasing the price of our facility. So we have to get to balance between the amount of batteries that we want to have and the depth of discharge that we want to get from our system. Anyway, considering the depth of discharge, the batteries can be classified into two groups: the batteries which are called light cycle and the batteries which are called deep cycle. Obviously, light cycle batteries have less depth of discharge than deep cycle. For light cycle, we can get a depth of discharge of about 20%, while for deep cycle we can get to an 80%. The point is that light cycle batteries are prepared for constant charge and discharge, but deep cycle batteries are more robust and have higher energetic density. Anyway, you can get information from the manufacturers which are at the bottom of this slide, for example Isophoton, Hopec, BAE, TAP, Tudor, or etc. So, talking about the type of batteries, we have to know that there exist several types in the market, but for PV applications, the most suitable batteries are the stationary ones. This type of batteries are designed to have a fixed emplacement and for the cases in which the consumption is more or less irregular. They are usually designed to reach deep cycles of discharge, but they cannot provide a very high current during a short period of time. Here in this slide you can find a table describing the main features of some types of batteries which are normally used in PV systems. We have added to this table the light cycle type of batteries for lead acid in order for you to compare between this type of batteries with the rest of them. But normally in PV applications we can use lead acid deep cycle, gel cell, or the new models for nickel cadmium. If you check the discharge depth, the highest one is the nickel cadmium one that can get to 100% of depth of discharge. But the lead acid one do have also quite a high deep discharge depth, getting to up to an 80%. Normally we have to know that gel cell batteries need less maintenance and can be operated in any position, so they are normally used, for example, in applications of traffic lights and for illuminating the city, but they are much more expensive than the lead acid ones. So for normal commercial applications we will use lead acid types. As we have said along the webinar, a diesel generator can be used as a backup in order to reduce the number of panels and batteries that we need to guarantee the supply after several days without sunlight, or in the situations of extraordinary consumption. As we will see in the next slide, nowadays the energy generated by a diesel group can be more expensive than the energy obtained from a PV system. So we will only use the diesel generator for extraordinary consumptions. Our goal must be covering the basic demand with the PV modules and just using the diesel generator for the peaks of consumption or for those periods that it happens that several days we don't have any sunlight. Anyway, it will depend on the price of the fuel in each country where we are considering the project. Here you can find an example of the price of the energy produced by a solar plus facility and by a diesel generator. Please take into account all of the notes that I am not going to read that are in the bottom of this slide. Some of them will be that the price are being written in euros. We have considered a radiation of 1,500 peak hours per year, and that we have got from we have calculated a diesel generator price of electricity of 0.35 euros based on the diesel price of 1 euro per liter. Please, you can write that down because I see it is not written in this slide. So this price of the diesel generator electricity comes from considering the diesel price of 1 euro per liter. This is an average price for Europe and some countries in the all around the world. So you can check that the price of an hybrid system is lower, much lower than the price of producing all the energy from a diesel generator. During the 25 years, of course, if we consider the initial, we have to consider the initial investment for the PV facility and then take into account that that facility will be producing energy during 25 years. The rise in the blue profile that you can see at the 12th year is because we are considering that after 10 years some of the elements in the PV facility will have to be changed. So now in the next chapter we will study the trends for this type of system, and we will go through different concepts like hybrid systems, efficiency optimization, and the new smart grids. So I'm receiving a news that we're going. Okay, so we're going to wait now for. We are going to do now the 3 minutes break, and please, you can remain connected because we are going to do now the break. And I can advise you when we are going to start with when we are going to follow with this presentation. Thank you. everybody. We are going to continue with this last webinar session. Now, as I was saying, we are going to talk about the nowadays trends for this type of systems. We are going to start with the hybrid systems with diesel energy and solar energy. Here you have a diagram on how these kind of systems work. You can check that the diesel generator is connected directly to the inverter with the alternating current bus, and how it works is that if the batteries get to a certain level of discharge, the inverter detects this level and it sends a signal to the diesel generator so that the diesel generator will start working and producing energy. The energy produced by the diesel generator, depending on the type of inverters and the manufacturer of the diesel generator and the inverter, can be used both for the consumption and to charge the battery, or just for the consumption. So it is important to know that the diesel generator that we have to use must have an automatic starter in order to detect the signal from the inverter. So every diesel generator allows this type of solution, and we have to check with the manufacturer of that diesel generator that it allows this type of inverters. Here you have an example of another hybrid system, which will be with solar energy and with wind energy. This type of solution is being studied in several research and development departments of many institutions and companies because of the good correlation between the wind and the solar resources, and also because both of the resources are renewable resources, so it is easier to get financial opportunities. We have to know that the difference in the connection between this system and the diesel solar systems, hybrid systems, are that in this case, normally the generators, both the solar and the wind generators, are connected by the DC bus instead of the AC bus, like in the case of the diesel generator. Well, there you have a chart at the lowest part of this slide, commenting which are the main features that we have to check in order to know if our location is favorable for wind generators or not. This chart is because, as you can read in this slide, there is not too much information about the wind resort in the different areas of the world. Normally we have to do our own study. Here you have a diagram of what we were commenting, that the wind generator and the PV generator are connected by the DC bus to the batteries. If we wanted to connect a diesel generator, that it exists also the possibility of combining wind, diesel and solar generators, we would have to connect the diesel generator directly to the inverter. This is one of the reasons why some of the inverters also included a charger, as we saw in the slide for inverters. Another good consideration in general is improving the efficiency in our consumption. Nowadays, we can find great evolutions in the consumption reduction of many massive devices. For example, the fridge, the air conditioning, and the lights. Especially in the case of standalone systems based in PV generators, This is especially important because the energy that is produced with solar systems is much more expensive nowadays than the energy for the grids, especially if we are using batteries. We studied during the rest of the webinar of this webinar course how the grid parity was going to be reached in the future. But here we have said that the solar system has a price higher than the grid because we are referring to stand-alone systems, considering also the price of the batteries, regulators, and this special kind of inverters. Anyway, continuing with this slide about efficiency in the consumption, we have to know that every standalone solar facility should begin by the optimization of its consumption efficiency. Here you have an example on how we can save 260 euros per year just by changing the fridge, just by getting a new fridge. The very old fridge used to consume 800 kilowatt hours per year in an average, and nowadays a new fridge can consume 150 kilowatt hours per year. This means a saving of 260 euros per year. Here you have some other examples on how we can improve our energy efficiency, our consumption efficiency, by changing different elements. Please modify the last row in the chart because it is wrong. Obviously, a personal computer with low consumption will need 70 watts, while the ordinary consumption for a desktop personal computer will be around 250 watts. It is important, if we are designing a PV standalone facility, to look that all the devices include their high efficiency level in their specification sheet. So you can see that the more efficient ones are those which are from energy class A. Here you have the example of a fridge. You also have the example of a LED light where you can save 10 times the consumption from an incandescent light, a normal light, and the example of the personal computer. Much more examples can be found if you get information from the internet, but those were the most typical ones. Also, in order to improve the final user's efficiency, there is a worldwide project known as Smart Grid. This project has been conceived with a global objective from the commitment of several international governments in the world, such as the European Union, and in collaboration with many other governments. The main objectives are to minimize the environmental impact, to reduce the dependency from fossil fuels by increasing the use of renewable energies, and to reduce the cost and increase the energy efficiency by giving to the final user more tools on how to improve their energy efficiency. For this project to succeed, they have established the goals of increasing the integration of renewable energies in the global electric grid and dealing with an intermittent and distributed generation, as you might know that the renewable resources are intermittent and distributed. So, to reach the goals in the previous slide, the governments have proposed the following mechanisms toward the smart grids. First, to improve the control and supervision of the generation, considering intermittent generation profile of the renewable energies, which makes difficult to forecast their production. Second, to improve the demand management, because nowadays there is a high peak valley ratio, as you can see in the picture in this slide, with a low correlation with renewable production. Some proposals include the use of electrical cars in order to reduce these peaks and valleys. Third, they are considering to improve the international grid connection. And fourth, they are considering to improve the electricity storage by investing in research and development of new ways of storing energy in situ, for example, with hydrogen or with new type of batteries. By the way, you can check this new Nobel Prize that has been given to a man that has won the Nobel Prize for inventing a new type of material that can have a very good applications in new batteries. It's an actual new. So we get to the chapter of the examples of applications for this type of solutions. About the applications areas for this type of systems, we have to know that normally there are zones which are distant from the grid, or zones which are currently being supplied by diesel generators. We can find a great potential for this type of system in the African countries, especially in those areas with the price of the fuel is high. Here in this slide you can find a map showing the number of people that do not have access to electricity in different parts of the world. You can check that the number in South Asia and in Sub-Saharan Africa are very, very high. So you have a good market in those continents. Application examples could be single-family houses, but it can also go up to public buildings such as hospitals or schools, public lighting and traffic lights. A lot of cities and countries are introducing and are settling their public lights with this kind of systems. Then we can get water pumping examples, which are very, very profitable for renewable energy supplying. And finally, we can get to desalination and water sewerage, and even industrial uses with the new types of inverters that can get to high power. Here you have an example of a project for water pumping, because it has great advantages to be fed with solar energy. Why? Because there is no need for batteries, no need for inverters, and no need for regulators. Nowadays there exist water pumps that can work with direct current, and also we don't need batteries because we can store the energy in a water tank in height. So the number of elements can be reduced just to the panels, the pump, and a control box, which will be provided by the pump manufacturer normally. This way we can reduce the price of the installation, and we also reduce the possibilities of breakdown. In Generalia, we do have a lot of experience with this kind of projects, and we can resume that they are very, very profitable to be performed. If any one of you has any kind of project, you can submit us the information. Well, other considerations to know about standalone generation is that we find nowadays limits on the system, because the maximum power output nowadays cannot be higher than 120 kilowatt peak. We have to check because each month the manufacturers are introducing new inverters and new batteries that improve this output power, but nowadays it can be higher than 120 kilowatt peak. Also, the maximum capacity of storage is limited by the batteries, and if we use lead-acid batteries, we cannot combine more than 4 blocks of batteries in parallel, and so we can only get to a maximum amount of batteries of well, as you can see in the chart at the top right of this webinar, each row has to store less than 144 kilowatt hours. So if you multiply this by 4 rows, you get that they can store more or less 560 kilowatt hours. We could use nickel-cadmium batteries in order to increase this quantity, this amount of energy, but we recommend to verify the information with the manufacturer, because these are new type of batteries for this application, and we have not used them yet. Anyway, as we have already said, we recommend you to check day by day with the inverters manufacturer, because they are working towards the system scalability in order to supply energy to growing populations, and with the introduction of mixtures of different types of energy, such as the wind energy, the hydraulic energy, and the solar energy. So we get to one of the final chapters in this webinar, which is the design of this type of installations. In order to design this type of project, we have to start by the study of the consumption, of the demand of our client. So we have to do a table like the one that you can find in this slide, studying which devices does our user have, what are the number of units of each device, which is the peak power for that device, which is the average power with considering a simultaneity ratio, how many hours are they using that device each day, and finally, how much is the consumed energy for each device per day. So for example, here we have taken a consumption from a typical house in a developing country, which will have 10 lamps, 1 personal computer, 1 fridge, and 1 television. They will be consuming 12,100 watt hours each day, and they do have a peak power of 1,500 watts and an average power of 728 watts. This average power is less than the peak power because, as you can see, the peak power, for example, from the fridge will be 1,000 watts, but the fridge motor will not be working the whole day. So the average power, we can consider it about 400 watts. We have to know that the peak power will affect the inverter calculation, the peak power for the inverter, and the energy consumption will affect normally for the storage system and the solar modules. So during the next slides we will study, based in the amount of energy that we have calculated in these tables, how to calculate the solar generator, the batteries, and the inverter for our PV project. For the solar generator calculation, we have to consider, we are going to consider the production that we got in the previous slide of 12,100 watt-hours per day. As we have explained already, we have to guarantee that this amount of energy is being produced during the worst day of the year. For example, in the case of Madrid, this would be in December. So, we consider that we are producing 2.4 watt-hours per day per kilowatt peak installed. So, if we consider the whole system losses, because we also have to include in our calculation the system losses of around 34%, this will mean a performance ratio of 66%. Then we get that the solar power to be installed must be 7,670 watt peak in order to get the 12,100 watt-hours per day. We insist that in this type of systems the performance ratio is lower than in grid-connected systems. If you remember, for grid-connected systems the performance ratio was about 0.75 and now it is 0.66, because we have to include the battery losses that we have estimated them around 15%. So, as we have to install at least 7,670 watt peaks, we could install, for example, 34 modules of 230 watt peak, which is a commercial size, in order to get 7,820 watt peaks of installed solar power. Then we have to calculate the battery. Now we have to also once more consider the 12,100 watt-hours that we are demanding each day as an average. If we consider in this example that the system will be able to store energy for 2 days without solar radiation, the batteries then should be able to store 24,200 watt-hours. So now we have to choose which type of batteries we want to use. In this example, we have chosen lead-acid batteries with a cycle depth of 80%, because we have already told you that these are the most typically used type of batteries for static energy storage. So, a good recommendation could be to consider a maximum discharge depth of around 60%, even if these batteries can get up to an 80%. We consider just a 60% in order to increase the battery lifetime. If we consider now the battery losses of around 15%, we will get to the formula to calculate the capacity, which is at the bottom of this slide. You can see that the capacity calculated in order to be able to give 12,100 watt-hours per day will be 12 batteries of 1,977 ampere hours. So, as a conclusion, as 1,977 ampere hours is not a commercial size, we can get 12 batteries of 2,000 ampere hours based in the C20 profile. This means that we are getting the profile that the energy will be discharged in 20 hours. We can consider that this is conservative, as in fact if we have introduced the consideration of getting the batteries functioning for 3 days, in fact, the battery will be discharged in a longer period than 20 hours, but then we will get even more energy from the batteries than the one that has been calculated. So it is better for us. Finally, for the inverter calculation, we have to consider the peak power of the system from the study of consumptions. So, if we go back to the slide where we had it, we can see then the maximum power would be around 1500 watt peaks. If we use a simultaneous ratio, that it means that not all the devices will be connected at the same time, of an 80%, we can get that the output power is a little bit lower than the one that we had estimated. Anyway, we will talk about this in the following slide. Sorry for mentioning it in this slide, because in fact it doesn't affect the maximum power, which is during a certain moment, but it affects the average power, which is included in the next slide. So in this slide, we are considering the maximum output power that has to be over 1500 watt peak. Here in this slide, we can see that if the maximum output power is 1500 watt peaks, as the manufacturer normally prepares the inverters to be able to double their nominal output during a certain period, for example, for the period that the motor of a fridge is working, then it is less than 15 seconds, we can consider that the power that we need in the inverter should be higher than 750 watt peaks. Now, by the other side, we have to consider the average consumption, and applying the simultaneous ratio that we were talking about in the previous slide, we can get then the nominal output power of the inverter should be higher than 728 watt peak. So, we have to choose the most conservative one of both limits. In this case, it will be 750 watt peaks, and then we have to choose an inverter with a nominal output power higher than 750 watt peaks. So, in conclusion, we have to know that for a demand of energy of 12,100 watt hours, we could use 7,820 watt peaks of installed solar energy, solar power, with a battery's capacity of 48,000 watt hours, and inverter nominal output power of about 750 watt peak. Anyway, we have to take into account the following observations about the design that we have done in this example. First, we have to consider that the consumption is homogeneous during the year, which is not a normal situation. Normally, we have to study the worst period of the year, but we can use a diesel generator to work as a backup during those days. So we are already out of time, but we are going to give some time for the maintenance chapter as fast as possible. Anyway, the maintenance is very similar to the grid-connected system, so we will need a periodical cleaning of the modules, depending obviously on the location, the pollution and the rain of each area, and we will have to check periodically the cable and connections and retighten the screws, And finally, we have to check the structure, especially if it is not protected against open air. It is very typical to find panel structures in this type of facilities which are not protected, and they get oxide because people are not using periodical antioxidant paint, and they get broken because of this. So please pay attention to check the structure state. And finally, we have to check if there is any new shadowing effect. Especially in the batteries, our maintenance, we have to pay special attention in the maintenance of the batteries, because they are a dangerous element that are not normally included in PV facilities for grid-connected systems. The main risks are the one identified in this slide, which are that the electrolyte is generally dilute acid, so it may produce burns if contacting with the skin or the eyes. We have electrocution risk, especially in wet environments, but if we are using 48 volts, we have also electrocution risk in dry environments. And as this kind of batteries produce hydrogen gas, we have also risk of fire or explosion. So we have to consider a place with appropriate ventilation. And we finish this webinar session telling you the main tasks that we have to check for the battery maintenance. We have to check that the room has been well ventilated and protected against the sunlight. We have to periodically check that the electrolyte level is between the manufacturer limits, and add distilled water in case that it is under the lowest limit. This is the most important thing to do in order to preserve the batteries in the best state. And we have to protect the connection terminals with antioxidant grades in order to avoid sulfurizing because of the acid and gases produced in the energy. And finally, we have to check the tightness of the battery connections and cover the terminals. So, with this chapter about maintenance, we finish with this webinar session. Thank you for attending this last session for PV off-grid facilities. Sorry, Fernando, did you want to say anything?
Yeah, okay, so yes, thank you, Javier, for this presentation. Thank you for this last session of this training module. So it was the last session. So here we close this training program. So thank you very much to our speakers for this excellent training session. Very illustrative, and hope this will develop and unlock the photovoltaic applications for all our audience. Well, today we cannot treat your questions, so you can submit them in the coming minutes, and we will give a written answer in the coming days. So thank you very much for your participation, and well, see you soon on Leonardo Energy with new learning programs. Javier, I give you the floor to say, well, your conclusions on the course. Thank you.
Okay, so well, thanks to all the audience of this webinar session and all the rest of the sessions. We have done 6 sessions. We have been really pleased from Generalia Group to be with you during all these seminars. And well, we thank everybody for listening to all the explanations that we have done. Anyway, we are open for any types of consultations or questions. You can find our information in the lowest part of this webinar session, or also you can get to know a little bit more about our company in our web page in www.generelia.es. And well, we are open to any interesting advice or consultation or question that you may ask us. So please feel free to write us about any project that you have. Thank you, Fernando, for working with us in this webinar session. We have found it really interesting, and we hope that we will see all the audience and you too in the rest of courses for Leonardo Energy. Goodbye to everybody.